Hello and welcome to Physics with Amol sir. This is part 4 of electric charges and fields. So I'm very happy to see that many of you are watching the videos, many of you are learning from it and you are asking your doubts as well. So before we start with today's class, what I want to do is I want to answer some of the doubts. Of course I've answered the doubts to these students already, but maybe others might also be having the same doubts, so that is why I want to clear them first. First was about the concept of quantization of charge. This is from the first part. So when you talked about quantization of charge, correct, maybe the concept is we are learning it for the first time, it becomes a little confusing. Let us see that one more time. What we mean by quantization of charge? We have a neutral object in front of us. Correct, neutral because the total positive charges and negative charges are equal. So there is no as such excess charge on this. How will you charge this? Two methods, either charging by friction or charging by induction. Correct. So when I want to charge this particular object, I have to transfer some electrons onto this object, or I have to take out some electrons from this. Correct. That is the only way to charge an object. There is no other method available. So let us say I am going to put some electrons. So if I put one electron on this object, it will get a charge of 1 electron exactly. Correct. So it will be 1.6 into 10 to the power minus 19 coulombs. After that, how much can we add? We can add one more electron. Now it will get charge equal to 2 electrons. 3.2 into 10 to the power minus 19 coulombs. Or you can put 3 electrons, or you can put 4 electrons. Correct? This is the meaning of quantization of charges. You cannot add half of an electron. Okay? Either you can add 1 electron or 2 electrons, so on and so forth. You cannot add 4.5 electrons onto this object. And neither can you take out 4.5 electrons from this object. That is called as quantization of charge. So whenever either charge is added or charge is removed, it is always in the integral multiples of charge of one electron. Okay, this is about quantization of charges. I hope that answers the question. Next was about, I showed an experiment where we rubbed a plastic sketch pen with a tissue paper, and I said that the plastic sketch pen has become negatively charged and the tissue paper has become positively charged. Of course, many students had the doubt why it has become negative and the tissue paper has become positive and not vice versa. Correct? For that, here is a list. Correct? This is called as the electrostatic series. Now what you see in this series, the materials which are on top, they are more likely to lose the electrons. Correct? And as the series goes down, the materials which are on bottom, they are more likely to gain the electrons. I'll give you an example. Look at the material of glass. Correct? Glass is on top, and 2-3 places before glass you will see silk. So if you rub glass rod with a silk cloth, the glass is more likely to lose electrons. So glass rod will become positive, and silk is more likely to gain electrons. Here silk will become negative. Okay? So if I rub glass rod with a silk cloth, glass becomes positive and silk becomes negative. But you will see below silk there is rubber. So if you rub silk with rubber, now silk will become positive and rubber will become negative. Getting the idea? So this is the electrostatic series. You can transfer charges from any body on the other body. Depending upon this series, it will be decided whether the material will lose the electrons or it will gain the electrons. Why they do so is because of the property, the configuration of these materials. Correct? So if you have material A and material B, one of them is more likely to attract the electrons from the other particular material. Okay? So I hope that answers the second question as well. So I urge other students also, whatever doubt you may be having, please make sure to ask so that I can address it. Okay? And when you ask one doubt, the doubt of other members also gets solved. Okay? Alright, so let us start with today's topic. So what we have done till now, we have talked about electric charges, we have talked about the Coulomb's law of electrostatics, and we have talked about the principle of superposition. Okay. Now we are going to move on to the next section, that is called as electric field. Okay. Again, very important. When we are learning electrostatics, as I told you, Coulomb's law of electrostatics, a very fundamental rule. Correct. Whatever we are going to study, we always come back to Coulomb's law. Then principle of superposition, again very important. And now next is the concept of electric field. Now what do we mean by electric field? Let us say I hold an object in my hand. Now this is not a neutral object. Consider this is some amount of charge that I am holding in my hand. Correct? So there is a charge equal to Q that is there present in space. Okay? Around this charge there is a region where this charge is exerting a force. That region we are going to call as the electric field. Okay? So once again, the space around the charge where it is exerting a force is called as the electric field. Now how do we understand whether there is an electric field? Okay, so as I told you, this will be our source charge. Correct? Some amount of charge Q is present on this object. Correct? That will act as our source charge. We will get a small charge. This is called as a test charge. Test charge Q. For this particular purpose, this is going to be positive and the source charge is also going to be positive. Okay. If this test charge is very far away from this charge, let us say 100 kilometers away, obviously there will be no force acting on this charge because of the test source charge. Correct? But as the test charge starts coming close, you will notice at some point there will be a force exerted on our test charge. Correct? Because their charges, they are going to exert the forces according to the Coulomb's law. Correct? So when the test charge comes at a particular point, let us say at a distance r, there will be a force exerted on our test charge. So this force divided by the magnitude of our test charge, that is called as electric field. So we write electric field as the force upon charge, that is the test charge, or we define electric field as force exerted per unit positive charge placed at that point. Correct? Obviously Coulomb's law tells you that if the charge is very far away, force will be less. So thereby you can say that if the distance is very large, the force will be less, thereby electric field will also be less. Correct? But if the distance is very small, if the test charge is very close, the force is going to be higher, thereby the electric field is also going to be higher. Okay, so once again, electric field is defined, electric field at a point is defined as force acting on unit positive charge placed at that point. Okay, now you will ask, what if the test charge is not present? If the test charge is not present, even then there is electric field present at that point. Okay. But why we require the test charge? It is for our purpose, so that we can measure the electric field at that point. Okay, so that is the concept of electric field, very important in the study of electrostatics. Okay, so this is electric field. Now, so what we understand, electric field, it does not depend on the test charge. It depends only on the source charge, the magnitude of our source charge. Okay, so electric field depends upon magnitude of source charge and distance from the source charge. If distance from the source charge is higher, electric field is going to be lower. If distance from the source charge is lower, electric field is going to be higher. E is equal to F by Q. Okay, and the SI unit of electric field is Newton per Coulomb. It is a vector quantity. Electric field is a vector. It has the same direction as that of the force that is exerted on the unit positive charge. Is that clear? So this is the concept of electric field. Another thing to remember about electric fields. Electric field due to a positive charge will be directed radially outwards, as you are seeing in the diagram. Okay. So if the source charge is positive, the electric field will be directed radially outwards, and if the source charge is negative, the electric field is directed radially inwards. Okay, so remember, whenever there is a positive charge, the electric field will be going radially outwards. If there is a negative charge, it will be coming radially inwards. Okay, now one thing that I forgot to mention, when we are talking about the test charges, okay, you can ask a question that why this test charge is not affecting the source charge. It is very much possible that it might. Okay, so whenever we are doing these suppositions, we are taking some things into consideration. What we are assuming? We are going to assume that the test charge is very, very small. Okay, it is so small that it is not affecting the source charge, because if it does, then the calculation doesn't remain very, very easy. Okay, so we make these assumptions to make the things convenient for us. Okay, now we'll talk about electric field due to a system of charges. So you will be seeing a diagram in front of you. Don't get confused, it looks confusing, but it's a very, very simple diagram. So what you are seeing in front of you, we have got 4 charges: Q1, Q2, Q3 and Q4. I think you are able to see them. And there is a point P. Correct? So we want to find out electric field at point P because of these 4 charges. So here we have the principle of superposition, similar to principle of superposition of charges. Correct? So what is going to happen is, at the point P, there are going to be electric fields due to charge Q1, due to charge Q2, charge Q3 and Q4. And they are going to give only one equivalent value of electric field. Okay, so at the point P, the electric field because of charge Q1 is given by E1 is equal to 1 by 4 pi epsilon naught Q1 by R1P square R1P cap in the direction of the vector R1P. Similarly, electric field at P due to charge Q2 is given by E2 is equal to 1 upon 4 pi epsilon naught Q2 by R2P square R2P cap. You can do this for all the other charges. We will find that the total electric field at point P is given by ER. We have used the word R because electric field is a function of position. So ER will be E1R plus E2R plus E3R, so on and so forth till ENR. Okay, and therefore the total electric field will be given by ER is equal to 1 by 4 pi epsilon naught summation of QI upon RIP square RIP cap. I goes from 1 to n. Okay, so this is principle of superposition of electric fields. So I hope the concept is clear. If you are having confusion, one thing I would suggest is you should go through your textbooks. Okay, so after watching the video, if you go through the textbooks, more doubts will get cleared. Now I want you to look at solved example number 1.9 that you will be seeing on your screen right now. The question is 2 point charges Q1 and Q2 of magnitude plus 10 to the power minus 8 coulombs and minus 10 to the power minus 8 coulombs respectively are placed 0.1 meter apart. Calculate electric field at point A, B and C as shown in the figure. Okay, so this is the figure that we are having. We have charge Q1, Q2. They are exactly 1 meter apart from each other. Then you will see 3 points A, B and C. We have to find out electric fields at these points. Okay, so just read the question, try to understand it. In the next class, we are going to solve this question. Okay, if possible, go through the text. Okay, try to see if it is making sense very well. Otherwise, next class we are going to discuss about this particular question.